Can you see my screen
Okay,
now?
yes, we can see your screen now.
And you can hear me too.
Yes, we can.
Okay, great. Yeah, thank you all for attending this webinar. It is nice to give a talk in the StatFin series. And this particular work also is very dear to my heart because I could collaborate with my college friend Anandamoy Mojumdar on this. I was trying to do something about this Granger causality in functional time series for a long time, but I'll tell you what the challenges were and where I got stuck, particularly because of the dimension of the data. And I was realizing that we needed to go Bayesian because that is where the dimension of the data is not so important, but of the number of parameters. But I was not equipped to do that, and that is where Anando came in, and we could do this together. So this is going to be the plan of my talk. I'll talk first about what is functional data analysis and about Granger causality. So those are the two things that we are trying to connect here. Then I'll give a brief introduction to yield curve, which is the financial application that I'll talk about. And since this is in a StatFin series, what kind of things we are trying to model and test for Granger causality. And then I'll present the model and how the data is. And then I'll describe the methods, the Bayesian methods, and finally some simulations and the result of the data analysis. So starting with functional data analysis. So what is functional data? The data itself, each data point is a function. So that is when we have functional data. So generally we use univariate data. And then we also know about multivariate, where each observation is a vector. So now each observation is a function. And these could be actual functions observed over time or space or some frequency. Or these could be also some functions that arise in the analysis, like probability density functions or dose response function, intensity function, things like that. So that is what we are trying to model here. And the standard book for functional data analysis is Ramsey and Silverman 2005. And this is an extension, as I said, of multivariate to functions. Each individual is characterized by one or more real valued functions rather than a vector in Rn, as is the case in the multivariate. So as with multivariate data, there are functional versions of analysis of variance, regression, principal components, canonical correlations, cluster analysis, classification. So all these things over the years have been developed for functional data. What is different? Why do we need another set of tools for functional data? Why is multivariate not enough? And the reason is that sometimes the functions have smoothness that we want to take into account, and that makes our analysis stronger. But more importantly, it is about ordering and neighborhood. So I'll explain this a bit. So in the multivariate data, if you have, say, a k-dimensional object, then if you just want to reorder those k dimensions, that will not change much, other than the mean vector and the covariance matrix, you have some permutations. However, in functional data, since we are assuming this kind of smoothness, and then neighborhood matters. So if 2 points are close by, then if you move them far apart, then you lose that smoothness, and then you cannot draw strength from that feature of the data. So that is why it is good to have different methods for functional data. And the first step that one does is, of course, you will have observations only at discrete points. Right? You will not have a whole function most of the time, unless you have some parametric form with, say, density functions and so on. So most of the time you will have observations on some discrete points in the support, and then what you do is first you smooth it with some spline or kernel or wavelet, some kind of approximation. And applications of this have been done in the climate sciences, land usage, electricity consumption, electrocardiograms, so various things. So this is kind of the mathematical modeling or setup. that you have n smooth random trajectories. So each trajectory is random. It is a random observation. We denote it by FIT. T is the support. It lies in this script T. And then for each observation, we denote it by I. So you have n observations. And each of them is coming from some process F that has some distribution on the space of functions. And throughout, we will assume that F is an element of this L2 Hilbert space. The observed measurements are available on a dense grid of support points, Tij, and we can lift this dense, we can say, even if it is a little sparse, that is okay, but we need to then do something about it. And then there is also scope for some observation error. So the observations are these Fi tilde Tij. So for the ith observation, you observe it as at these points J, Tij. So there are m observations, and this m actually can also vary with I. So for each individual, you can have varying number of observation points. But then you also add some error, which has mean 0 and some fixed variance sigma squared, and also uncorrelated with each other, uncorrelated with the signal. And that is Fi tilde, which is observed. Now, most of the development in functional data has been with independent and identical replications of the data. So when I say independent, within each I, the Fi Tij can be dependent for different T's. Okay, so within each individual, the observations at different different points can be dependent, but each individual is independent from the other. So that is what this means. So across I, they are independent. And this permits the use of information from multiple data values and identify patterns. However, in certain situations, it is unrealistic to assume that the functions across time are independent. And I'll tell you a little history of how I got into this. So my first work on functional data was with volatility, and I was looking at the spot volatility over a particular day. That was my function. So the day, each day was the support of the function, and at different points on the day I had the spot volatility, and I was trying to model that, and we did, and it also got published. But the main problem that we had convincing the referees was, why am I considering the observations across different days to be independent? So volatility tomorrow is dependent on volatility today. So that is when I did this next work on time series of functional data, and that is where I used the yield curve for the first time to model the yield curve as a time series. So I'll talk more about the yield curve later, but this is the time series of functional data where across I do not assume independence, but there is this time series of functions. So you will see that this looks like an ARMA model, except that each Fi is now a function. Okay? And I denoted this by ARMA H because they belong to the Hilbert space, so that is the H. And then epsilon I are, that is from the moving average, and eta I is the white noise. And thetas are some linear functions. So they are taking a function and mapping it into another function in a linear way. So those are the thetas. So next, let me talk a little bit about Granger causality. This is a more, I think, common concept in functional data. So this was originally introduced by Wiener in 1956 and formulated by Granger in 1969. So given two stationary time series, let us think of just univariate series. If the variance of prediction error of the second time series is reduced by including past measurements from the first. So this is in words, what that means is you are trying to predict, let us say, the series y. You can use the past of y to predict future values of y. You can use the past of y and the past of another covariate x to predict the future value of y. Now, does including the x in the prediction improve the prediction? Okay, that is the concept of Granger causality. So if it does, then we will say that x is Granger causing y. Notice that this is different from correlation. We are not including, so for predicting the value of yt plus 1, we are not looking at xt plus 1. We're looking at values of y until t and values of x until t. So that is how it is different from correlation analysis. So we're looking ahead in one of the variables and not in the other. So this in multivariate time series was developed by Geweke, and here we will extend that to functional data. So consider a vector time series that has an autoregressive representation, and suppose this z can now be partitioned into x and y. That is what I was saying in words, but I was saying about univariate. Here x and y each is a function, and then we're interested in the Granger causality of y on x or x on y, either way. So one of those or both maybe. So x has an autoregressive representation, and then we can partition the linear projection of xt on xt minus 1 and yt minus 1. So this is the first model where xt depends only on the past values of x itself. This is the second model where x depends on the past values of x as well as past values of y. And then we test whether this variance is reduced in the second model from the first significantly. If it is, then we say that y is useful in predicting future values of x in addition to what the x series already provides, and therefore y is Granger causing x. So that is the definition. So next we go to the yield curve. So what is the yield curve? It is also known as the term structure of interest rates, and it represents the relationship between spot rates of zero coupon securities and their term to maturity. A lot of words. What this means is that what is the support, the capital tau, capital T that I was talking about, the support is different maturities. Okay, and for each maturity, you have some interest rate. So if you put money in the bank, you will get a different interest rate depending on whether you are keeping it for 3 months or 1 year or 10 years. Okay, so that is the function. So the function is of the maturity. And then for each day, you have a different set of interest rates. So this is a time series of the interest rate curves. Okay, the yield curve is over different maturities, and then you are looking at it at on a different days. So the day is the I that I was talking about before, and the maturity is the T that I have. So we look at the yield curve of two different economies, USA and UK, and we check if one is Granger causing the other or not. The reason that we suspect some causality is because they are operating at different time zones. So information on one is available before the other, and therefore it may be that when you have something happening in the UK market, that information may percolate the US market when it opens, and that might change the interest rate there. So that is why we suspect there may be some Granger causality here, and the other way around. So that is the data set that we've considered. And both of these data sets are available freely, publicly. So just to show you how the data looks, this is the raw data of US interest rates. So on the x-axis is the maturity, and on the y-axis is the time. So those are the different days, and the z is the yield, the observation. Okay, so the interest rate itself. So for the first day, for example, which is the frontmost curve you see, and that is the first day, different maturities, and now you have it for every day. So this is 2019, and this is how the data set looks. Now, there have been several modeling approaches to yield curve before. There was the no arbitrage approach, where one perfectly fit the yield curve at a point of time, avoiding arbitrage. And then there is no question of evolving over time. So it is just each of these curves is fitted with no arbitrage conditions. The other is the equilibrium prediction, where the instantaneous rate is fitted using affine models, and then the other maturities are derived under assumptions of risk premium, which means the for different points of time. Okay, so for different days, you model the instantaneous rate, the spot the interest rate for 1 day kind of thing, and that is done by affine models, and then you use theoretical models on risk premium to model the other weights. So it's kind of like the two traditions. One of them is modeling only along the x-axis and the other is modeling only along the y-axis. And there was no unified approach for both of them. And this was done in 2006 by Diebold and Lee, where they used factor models, and the basic functions were of what is called the Nelson-Siegel exponential components, and this is actually very broadly used even now. And so these were kind of like the basis functions, and based on that they model the time evolution of the functions. So 2019, this is my paper with Claudia Kluppelberg, we developed a non-parametric model based on functional data. So we did not assume any standard basis functions, but we allowed data chosen basically based on the covariance matrix, principal components of covariance matrix driven support functions. And then we also allowed the scores to evolve as ARMA processes, whereas in the Diebold and Lee, they were letting the parameters evolve individually as AR1. So they did not allow dependence among the parameters, and the MA was not there. So it was a lot of development on the Diebold and Lee, and we did get far better fits. So that was time series of functional data and how that was applied to yield curves. So now I go to the main thing in this paper, that we want to have a Granger causality test for functional data. So we have multivariate functional AR models. So the multivariate is because of we are having multiple functions. Okay, and then like in the model I talked about x and y when I was presenting the Granger causality. So you could have multiple of them, and then each of them is an ART process with the mean function mu, and epsilon is the vector of innovation functions, and each epsilon is a sequence of random functions, mean zero random functions. Okay. And there is a fixed covariance matrix. And the psi is a linear operator on L2. So it is taking one function and mapping it to another function. But it is a linear, we're assuming it to be linear. So we assume that each function is observed at unequally spaced points, tau n. We restrict to p equals 1. So we'll just do this for AR1 and only consider integral operators for better interpretability and computational convenience. But the theory actually can be developed for more. And in practice, functional observations are observed via discrete samples. This is true for, I already presented that for functional data, that you have observations at discrete points of time and also with some measurement error. And the same things we assume for this data set too. So we have observations y, I, t, n. The I is for the ith day, remember, and t is for the tth maturity. And then there is the error. Okay, so and n is from 1 to k. So because I could have multiple functions. So in the univariate setting, I did not have this n before. I have this n now because I've shown you the x and y, but it could be other multiple predictors could be there. So that is why I have this n from 1 to k. So I can have n functions. Each of them, or together, they are functional time series. So in the usual univariate setting, and this is where I said in the very beginning, motivating, like why I had to go Bayesian, that the usual way of testing Granger causality is you look at the forecast sum of squares error, and from each model, and compare them through an F test. So this, wherever I had this Granger causality here, so you think of this as univariate, then you will have a variance of u, the sum of squares error for u ultimately after fitting the model, and you will have one for v, and then you compare these two variances. So not multivariate, but just univariate. So you have two scalars, sum of square scalars, you will compare them with an f-test and see if that is significant or not. Okay, that is the standard way of doing Granger causality. But now I have this covariance matrices, but they are infinite dimensional matrices, right? Because each of these is a function. So I really have these covariance functions. So for multivariate, one can extend the univariate f-test by taking, say, the trace or determinant. And this kind of works for low dimensions. But as we all know, if we go to high dimensions, the covariance matrix becomes unreliable. And now we are not even going to high dimensions, we are going to infinite dimensions. So looking at this, that is what I first tried, looking at this, trace of the covariance matrix or some kind of trace kind of thing for infinite dimension. But it was too noisy in the simulations. It was not giving good results. So I realized that the problem is that the dimension of data is becoming large and the f-test is becoming unreliable, as the estimation of the covariance matrix is not efficient. So this is observed in high dimensional covariance already, and I now have infinite dimensions. So that is why we had to look into Bayesian procedures which concentrate on the dimension of parameters and not of the data. So even if the dimension of data grows, if I do not have too many parameters, if I can model them with a fixed low number of parameters, I'm fine. There is another issue with using the measurement error model and ARMA things. That is that the presence of measurement error increases the estimation error of psi and produces inefficient forecasts. And this is the proposition that says that if you have the y, which is functional ARMA, and functional AR, and so this is an AR model, not NOMA. And suppose we observe it with error, which is independent white noise, then the observed process has a functional ARMA of order PP. So you're starting with the functional AR, but just by adding the noise, the observed process becomes functional ARMA. So that is a problem, right? Because we will be proceeding with everything being AR, but that is not true. So this was proved theoretically by Koval 2019. So that means that the multivariate functional AR is inappropriate. So to overcome this misspecification, we separate the observed data into functional process and measurement errors in a dynamic linear model setup. So that is the motivation of the DLM setup. So these two slides are basically about the motivation of why we are doing things the way we are doing. This is why we are doing the Bayesian, that the parameters, the number of parameters remains under control, and we are going through DLM because we want to separate the evolution of the data from the noise, and DLM is kind of a natural way to model that. Okay. So actually, we relied a lot on this Koval, Madison, and Rupert paper, where they propose a hierarchical model for multivariate functional time series. But theirs was there was no Granger causality there, and sorry, it should not be multivariate. It is just functional time series. So there was a univariate setup, and we extended that to multivariate. So this is. So yeah, here I say we extend that to the multivariate setting. So there was the univariate functional time series. So we assume that alpha t is yt minus mu, then this is the measurement of, this is the specification of the two-level hierarchical model. So we have y evolving as mu plus alpha plus an error term v. Now this alpha itself is the functional autoregressive model. And yeah, so functional autoregressive of order k. So alpha depends on the past up to t minus kth term. So this is the two-level hierarchical model, and we represent this as a dynamic linear model. We will use the observation equation to discretize the functional data and obtain the measurement error. And then the evolution equation takes into account the correlation among the functional time series and define the process model. So, and then we will employ efficient Gibbs sampling to perform inference and prediction. And for practical implication, we select a finite set of evaluation points for each functional time series. We will also need to discretize, so approximate the integral. So we have this integral here. We approximate this with quadratures, with the known quadrature weight matrix, and let Z be the incidence matrix, which means that because we will have everything in a matrix setup. So I'll just go into the So here Z is the incidence matrix, which means that if we are looking at the Tth observation, then those, here I have the Z, then those will be ones and the others will be 0. So Yt is Zt mu plus, so I'm writing this as a big vector of appending Y1 and then Y2 and so on. So Yt is Zt mu plus Zt alpha t plus Vt, and Vt are independent normals with.
Hello, I can't hear you.
Sorry. Can you hear me now? Hello?
Yes, you are audible.
Okay. Vt is modeled as a multivariate normal, and then alpha is the autoregressive model, and we are taking just autoregressive of order 1, as I told you before, but you can easily extend this to autoregressive order p. It just notationally more cumbersome, but theoretically there is no other problem. And then epsilons are again assumed to be independent normals. So these are my priors, and then I will take hyper priors on those. So this is the notation. Let's not go into the detail too much. This will be
Sorry, Rituparna, I could not hear you for last couple of minutes. I'm not sure whether that is the same case for others. If there is a case, then could you please repeat for last couple of minutes?
Okay. So
Ananya, maybe I just ask another participant. Ananya, did you also face the same difficulty?
No, sir. Actually, she is audible.
Okay,
Oh.
then it was probably from my
Yes,
side.
audible.
okay, then I'll just continue. Yeah, so let's not go too much into the details here. The paper is accepted and it's also on archive, so you can look at the mathematics there. I'll just try to give you the idea of what's going on. So we model the Y as a functional AR of order 1, and write the model as partitioning into linear projection into Y and X. So this is the full model, okay, when Y depends on both X and Y, the past of X and Y. And epsilon is a zero mean independent random functions with covariance matrix K epsilon. This K epsilon given here. And Y depends on both Yp minus 1 and Xp minus 1. And this is the restricted model where Y depends only on its own past and not on the X. So in this setting, X is said to Granger cause Y if model M1 is significantly better than model M2 at forecasting future values of Y. Okay, so model M1 is the full model. If it is significantly better at forecasting future values of Y than this restricted model, then there is Granger causality. So model M1 and M2 are of the M-far form, but then we will convert this to the DLM form. And that is what we do here. So let θ1 and θ2 be the vector of parameters corresponding to M1 and M2. And these are θ1 and θ2, these are the parameters, the mu, sigma, psi, and k. And then we will have to put priors on these parameters. So the null hypothesis is that both models are kind of the same. The alternative is that the past of X brings in more information. And what we will use here is what is called the Bayes factor. So the Bayes factor is central in Bayesian hypothesis testing. It is the ratio of the marginal data densities for the two hypotheses. Okay? So let PYTM1 is the marginal of YT. So here we integrate over all the parameters and we look at the marginal of the data, and that under the first model, and the ratio of that to the marginal under the uh, other model. And for reference, you can look at this and Raftery 1995 paper. So this is what we are looking at. So you can see that if the marginal density is significantly higher in one of the models, then of course it is much better. Now, Bayesian hypothesis testing begins by specifying different prior distributions, and we also have the likelihood of the data given the priors, and then we have to compute the marginal of the data. So you have to integrate away the parameters. And so for computing this, we will apply what is called the modified harmonic mean approach. And I am describing that here. So let theta be a k-Fairchild factor of parameters corresponding to the model. And first we obtain sample draws from this theta, from the distribution of theta. And ns is the number of samples. And we draw this from the posterior distribution. So we have the prior, we have the data, we can obtain the posterior. From the posterior, we are taking sample draws. Now the marginal of the data is computed as this particular thing, where you take the likelihood and multiply it by the prior. So on the bottom, this is the joint distribution, and on the top, we have H. I'll just tell you in a moment what that H is, and then you take the average, and this is one way. So this is essentially you want to integrate over the prior, but integrating itself is a huge task, and we are looking at a big parameter space. So this is one way to make that more efficient. So H, I have misread H. So H is essentially a multivariate normal with the same mean and covariance matrix as the posterior. Okay. So this is on the bottom is the actual, is this the joint, and on the top it is the a multivariate normal on the parameters themselves. Okay. So we specify the prior distribution suitably, and we have chosen the priors to be proper priors so that posterior sampling becomes a closed form, known distributions, so it is easier to sample from there. The hyperparameters of the prior are chosen in such a way so that the prior variance is very large, which means that the priors behave as flat priors. We are not putting in more information than we need to. More subjective information. We're trying to keep this as objective as possible, so making them flat priors, giving a very big variance. And so this strategy makes the posterior inference entirely data driven and reduces the sensitivity to prior choices. And again, further details are in the paper, exactly what priors we are putting and all that, all the computations there in the paper. And then we have to look at the likelihood. So this is the prior, and then we have to look at the likelihood, put them together, get the posterior. So the likelihood is from the dynamic linear model that I have already presented. And then for one step ahead distribution of y from the DLM, we can get that since we're starting with normal, we get another normal. We only have to take the conditional mean and the conditional variance, update them step by step. And the predicted state estimates are also given. So DLM analysis is quite standard, and we could derive these steps from there. So, and the equations at the update stage are also given here. So finally, we will use Gibbs sampling to obtain the posterior, to obtain draws from the posterior. We first initialize the DLM parameters and later we use the sampling distributions. Now the algorithm to compute, so I've talked about a lot of things. So here I summarize the algorithm to compute the base factor, translate the models M1 and M2 to DLM form, consider model M1, and we'll do the same thing with M2. So initialize the parameter space, and then for every simulation, you obtain a sample by applying the posterior sampling distribution and substitute this posterior sampling to obtain the prior density function at that particular point, at the sample point, compute the likelihood at that particular point, and then also the H, and compute the base factor. You can do it again and again and get the sum and obtain the base factor. And then repeat the same thing for model 2 and not the base factor, sorry. Here you find the marginal of the y for the model 1. And then you do the same thing, find the marginal of y under model 2, and then that ratio is the base factor. So interpretation of the base factor. Of course, when you go Bayesian, you don't really have, I said the base factor should be large or small, and how large. So there are no standard distributions or cutoff values because we're looking at the parameters now. So Cass and Raftery provided an interpretation of the base factor in terms of evidence against the null hypothesis, and these are presented in table 1. So if the base factor is between 1 and 3, then there is not much of an effect. If it is between 3 and 20, then there is substantial effect. 20 to 150, it is strong, and greater than 150, then it is a decisive evidence. And of course, the base factor could also be less than 1, as we will observe in some cases, which means that actually the restricted model is even better than the full model. And that is one thing that really puzzled me, because being a frequentist, I couldn't think how a bigger model could be worse. But then I realized that in a Bayesian setting, the model itself can be worse. It is not about how much evidence you're getting from the data and so on. So it is just a worse model to fit the data. Okay, so we consider 2 simulated cases. One, yt is generated from m far and xt is generated from far, and we check whether the xt causes y. So this is really, the first one is the dependent case. So y actually depends on x, and in the second case they are independent and each is a functional autoregression. And then we repeat this simulation 40 times. I know this is not too much, but it was taking too long, so we just restricted to 40 times for each of the dependent and independent cases, and computed the base factor. And even with 40, we saw a clear signal. So what we present here is a box plot of the logarithm of base factors. So for each data set, we are getting one value of the base factor. So I have 2 box plots that I'll show you right now. One is when you are generating from this model 40 cases, and for each of these 40 cases, you will obtain the base factor and the box plot of that. And then in the other one, the box plot of these ones where they're independent. And you see that the data are, the results are quite, the distributions are quite well separated. So what that means is that our test is indeed able to make separation between the dependent case and the independent case. So that was encouraging. And then I think finally I will present the real data analysis. So this is the data on yield curves for USA and UK, and we looked at 5 months starting from January to May 2021. There were 82 functions for each data set, and the values of yield curve were available for 9 maturities, and these are the maturities in months. So we will obtain the USA bond yield of T maturities from US Department of Treasury, and the UK bond rates from investing.com. So both of these are available freely. We performed 1,000 simulations to generate the posterior sample. So there was this capital S in the calculations on how many posterior samples generated. So that is the number. And the dimension of the parameter space is 123, just to give you an idea. And so we checked both relations, whether the US yield curve is Granger causing the UK yield curve, and again the other way around, whether the UK yield curve is causing the US yield curve. And what we see to our disappointment is that none of these causes the other. So both of them were insignificant, or in fact, one of them was negative, as I was saying that it could be negative. So the model without using the other is actually better. Okay, so actually both of them are negative. So using the other just introduces more noise, and it is a worse fit. So it's a worse model, rather, not a fit, a worse model. So it's better to use only that country's past and not go into the other country. But of course, we wanted some, test where the hypothesis was rejected. So we looked some more, and we wanted to do this on air pollution and meteorological factors. And since I'm presenting it this way, you already know that the effect was there. So I'll just describe the data. What we do, we investigate the causal effect of meteorological factors on air pollution. What are these specific things? So for air pollution, we are looking at the particle pollution levels, particulate matter of diameters 10 micrograms and smaller. This is a standard pollution indicator that is used, and this is denoted by PM10. We use data in the city of Delhi because it is known to be bad for pollution, and then daily data from January 2015 to June 2020. So there were 2008 days. We had to discard some days because of the data was not very clean, and still we had 1670 days of data. And this was downloaded from the official Central Pollution Control Board of India website. And then, so that is the YT, that is the variable that we want to predict. And then the explanatory variables are meteorological factors. So first, let me show you the data. So this is different days, and this is the time of the day. So we're looking at a function as the time of the day. So that is the function. And then for every day, we have different functions. So that is how the data looks. And for X, we take the daily average of three meteorological factors: temperature, relative humidity, and wind speed. And these were obtained from a company called Meteo Blue. And they do charge money for providing, but for research, they gave it to us for free, as long as we mentioned them. So in this case, xt is not a function. Xt is actually just a vector. But that is okay. All the things that we have done, in fact, they become simpler when we have xt as a vector. But the y is still a function. So we have to go through all the functional data things, functional data machinery. But it is a little simpler because x is itself a vector. And for this data set, the parameter dimension was 361. And we had data for 1670 days. And in this case, the logarithm of the base factor was obtained to be 78. So let us look at this table now. So 78 for the logarithm of base factor means there is a decisive evidence against H naught. So there is definitely Granger causality in the pollution level of Delhi. Essentially, what that means is if you want to predict the pollution level of Delhi, the whole curve for a whole day, then in addition to taking the past curves, if you also take the past meteorological factors, then your prediction will improve a lot. So that was our conclusion. And I think that is the end of the talk. Here is my email if you have further questions. The yield curve time series paper is this 2019 paper, and then the recent paper on Granger causality, it has been accepted but not published yet. So thank you.
Thank you very much, Rituparna. Any question from audience? Questions or comments?
So may I ask a question? Am I audible?
Yes, sure, Ananda.
Yeah. So this yield curve data, where did you find it? Means, what is the resource?
Yield curve is available online. So for the US, it is in the Treasury, and for the somewhere I must have mentioned it. Analysis. So US Department of Treasury, and for UK we got it from investing.com.
Okay, thank you.
Are there any more questions? Okay, then we will meet again in a couple of minutes for the next talk.
So I want to say
So,
thank you, Rituparna, for a very nice talk.
Thank you.
yeah, thank you very much. Yeah. So we'll return in a couple of minutes. So the next talk would start from 7 p.m. in Indian time.
Sorry, may I make a question about a technical question?
Yeah, sure. Let me check if
Is this to me?
speakers.
Yeah,
Yes.
I'm here.
No, it is to the organizer because so I'm sorry.
Sure.
Because I don't know, I don't see the option for sharing the screen for presenting my slides. So perhaps you have to habilitate me.
Let me check. So first, you check that in the bottom when you have this
Yes, I did.
microphone and hand raising, and there that do you find upside arrow?
Yes, upside arrow. Okay. So entire
check
screen.
if that helps.
Tab, present. So your entire okay, a tab, a window. Okay. So what do I share? The only a window? What do you usually do?
Okay, so what I generally do is that I first open my slide file, if that's PDF or PowerPoint,
Yeah.
whatever.
Yes.
So that is open somewhere. And
Yes.
then if I click the middle one window, then I get
The window.
an option where many open windows,
Okay.
all open windows will be there. So I would choose what I would
Okay,
like to share.
good. Let me try. I'm not sure. No, this is not good. Okay. Can you see? Yes, I can see. Okay. But if I want to
Yes, we can
make
see.
Control L, no, Control L is not good. I want to show, no, it was F11.
F11.
Okay, so I don't see you anymore, but I see my full screen. Do you see?
That's okay, yeah. So we can see.
Okay, good.
This will work.
Okay, so I wait when we start again, and I
Sure.
will do this. Thank you very much.
Okay, yeah. See you in a couple of minutes. Hello. Okay. So this is time. Now it is 7 p.m. according to Indian Standard Time. So it is the time you can start the second seminar. Before that, let me introduce briefly Professor Mancini. So here, so so Professor Mancini, I mean, may I continue recording? I mean, would you allow, or should I stop recording?
Sorry, are you asking to me?
Yeah, I'm asking before starting your talk, should I continue recording or should I stop recording? Because this presently it is being recorded.
As you want, as you want.
Okay. Okay, thank you very much. Professor Mancini has completed her degree in mathematics from Pisa, University of Pisa and University of Paris 6. And after that, she completed her PhD in mathematics from University of Roma Vergata. And now she is a full professor in University of Verona, Italy. So it is my pleasure to invite her to present a seminar here. Today, she'll be talking on warning about future jumps, properties of the exponential Hawkes model. So I request Professor Mancini to start, and can also say something more about herself if you.
Okay, thank you. Okay, the work I'm going to present is joint with Rachele Foschi in University of Pisa and Francesca Lilla in Bank of Italy. So why, what motivates this paper? When we, okay, I am dealing with modeling financial asset prices. So, and in particular, jumps occurring in financial asset pricing, financial asset prices. The problem here is the following. When we observe a cluster of jumps, that is an accumulation of jumps in the price evolution of a financial asset, we wonder whether these jumps, this cluster is yet exhausted or is going to continue to produce jumps. Okay? That is, since jumps represent particular high turbulence in prices, we ask whether the turbulence is going to finish quickly or it's going to continue. In particular, many financial crises, like for instance as the Lehman Brothers default in 2008, have been preceded by unusual turbulence in prices. So not only an increase in volatility, but also in the presence of jump clusters. So, in view of this, one asks, is it possible to exploit the observation of a cluster of jumps to improve the measurement of the probability of the occurrence of a further jump? Okay? And how probable is the occurrence of a cluster of jump? These phenomena are related to the behavior of the inter-arrival jump times, so the durations between consecutive jumps, and how these durations are linked among each other. So let us see how in the literature asset pricing models with jumps have been considered. Starting from Merton in 1976, many papers used jump diffusion extensions, jump diffusion models, extensions of the Black-Scholes asset price model, where the price path can jump finitely many times within a finite time horizon, and the jump part of the log price is a compound Poisson process. So the sum of jump sizes from the jump number 1 to the jump number, the number of jumps occurred until time t. N is a jump counter in the Merton model and in all these strands of literature with independent increments. So the jump inter-arrival times are independent. So the jumps cannot usually cluster. To better explain observed clusters in practice, since about 2005, the compound Poisson process was replaced using a more general Ox process, both for models in finance and for models in insurance. In particular, the exponential Ox model is the most used type of Ox model. This has an exponential kernel, we will see. So what in the literature now we have a lot of formulas, available formulas. Using those formulas, we could compute moments of an increment of n, the Ox process, or an approximation of the law of such increment, or the probabilities of for the number of future jumps in an interval, but we cannot calculate the probability of the events we are interested in. For instance, the occurrence of a given number of jumps in consecutive observation intervals that we will see later. Okay, so what we did is investigating new properties of the exponential Ox model, allowing to find the probabilities of our interest. That is, the probabilities of future jump arrivals conditionally on having observed specific configurations of jumps, of previous jumps. This clearly could be could give indications in assessing the risk of a financial asset. So in managing our portfolio decisions, clearly provided that the model is consistent with the prices, the jump arrival of the price, the jump arrival. Okay, we found new formulas. We checked on simulated data whether this formula give good indications about the true probability, because we will estimate the parameters of the Ox model and we will use the estimated values in the formulas. So we ask how much error we do in calculating the probabilities with respect to the true probabilities. And we applied the formulas to empirical data consisting of jumps filtered from discretely observed prices of the JP Morgan asset, and obtained the quantifications we were looking for. So this is the framework we have in mind. X is the log price of an asset, and we assume it evolves in time like following this stochastic differential equation, where we have a trend, A t dt, plus Brownian fluctuations representing usual market activity fluctuations around the trend, which are amplified or reduced by the coefficient sigma, and jump part representing the unusual fluctuations, possibly abrupt, possibly large, for instance, unexpected reactions to macro news. We can observe the asset price discretely. For us, delta will be 5 minutes, not to incur, for instance, in microstructure noises, which would make this model not proper. The jump arrivals is modeled like this. Similarly as in the compound Poisson process, but now N is a Ox process. So here, tau are the jump times of this process J, Y are the random sizes occurred at time tau I, and N is the counting process of the jump arrivals. In order to capture clusters of jumps and whether a cluster is going to generate a further jump, we use a Ox process for N, where the arrival of one jump of each jump increases the jump intensity, thus increases the probability of the occurrence of further jumps. Aizzalia, Caccio Diaz, and Levin, 2015, adopt a multivariate version of this model with specified dynamics for the volatility coefficient sigma. But they look for moments of their process. So they look for, they have a different goal with respect to us. Okay, what is a Hox process? It is a simple point process, so where at each time, at most one jump can occur, having intensity like this. Intensity is defined as the probability of having one jump conditional to the information, one jump in the interval from t to t plus dt, conditional to the information up to t minus, okay? Relatively to the length of the interval, okay, this interval. Lambda is specified with respect to a filtration. We consider here the filtration the natural filtration of the point process generated by n. So in the Ox model, lambda is assumed to be of this form. A baseline level lambda 0, that would be the level of a Poisson process, but this time plus the integral up to time t, lambda t up to time t, of a kernel function evaluated at the length of time from S to this t in the NS. This amounts to lambda 0 plus the sum of phi at t minus tau L, where tau L are the jump times. So each time a jump occurs, this sum increases by one element, phi of something. Lambda 0. Can you see my cursor here?
Yes.
Okay, good. Also the highlighting. You can see also the highlighting like this.
Yes.
Good.
Yes. Good.
Thank you.
I can also see something like on the top right corner, a black box. I don't know whether others are also seeing that.
The top
So,
corner, you
Yeah,
can
yeah.
I can also see that
Oops.
covering the slide.
Sorry, I didn't hear.
nice.
I didn't hear. Do you have problems in seeing here?
Correct. Yes, this top right corner is blocking. This black rectangle is blocking your slide.
This one.
Can you shift to the bottom?
To the bottom, yes, I can go here.
Okay, fine. The top right corner, this black rectangle, could you shift to somewhere else? No, I think you don't see that thing. Okay, so no problem.
Let me see. Let me see here. This one.
Yes, this one.
What's that? Why? Perhaps if I do this, no, the same. What's that? Conformità, il file corrente è conforme, non visualizzarlo più. Let me see. It is possible that it stopped. No, it didn't stop. Cancella.
Okay, it is not. It blocked.
Okay, now it's okay, right?
Yes.
Okay. Sorry, I'm very sorry. Thank you.
Okay,
so I hope you could understand up to now. Can I do, or do you want I come back?
No, this is all fine. But the rectangle is still there, but don't worry. It is not blocking much. So
it's still there, I think.
Yes, I see. Ma perché? Abilita, modifica, disabilita. Perhaps it's safer that I check. Look, I will keep this because in this way I can see when it appears. Otherwise, I cannot see. So I keep not full screen, so I see. Sure. Okay, but it's better. Okay. I want to enlarge this. Okay. So, lambda 0 is strictly positive. The kernel function satisfies some regularity, integrability conditions, and is positive, and phi of 0 has to be positive. I will show you why. And we take n 0 equals 0, no jumps at 0. Then, how the lambda evolves. At time 0, its value is lambda 0. And it is, the value lambda 0 is kept until the first jump time. So it is constant until tau 1. Just after tau 1, it jumps up by phi of 0. So you have self-excitation exactly when phi of 0 is strictly positive. So lambda increases after each jump time. And this increases the probability of further jumps. For t between tau 1 and tau 2, the next jump, lambda keeps only this term here, and usually this phi is a decreasing function when t minus tau 1 increases. So lambda jumps up after tau 1 and then starts to decrease until when the second jump arrives. The second jump arrives, then another phi of 0 is added to lambda, and so on, and then starts to decrease again. So this is a picture in the special case of exponential Hawkes process, where phi is an exponential function. So we have lambda 0 up to time tau 1. It jumps up just after tau 1. Note that the path of lambda is continuous on the left. It jumps up, then then lambda decreases. Then, as soon as another jump occurs, it increases again by alpha, phi of 0, and so on. Okay. From the branching processes perspective, N can be seen as the superposition of two jump processes. A simple Poisson process with the parameter lambda 0. The jumps produced by these Poisson process are called father jumps. The other jumps are called descendants because they arrive when lambda is at a level higher than lambda 0. In our model, we interpret the fathers as sporadic, independent jumps having not persistent causes, okay, like a Poisson process. The descendants are jumps generated by some previous jumps, okay? So jumps having being part of a persistent phenomenon. Okay, what did we do? We obtained the following three results, theoretical results. So we defined the end of a cluster of jumps in terms of the intensity lambda, which is useful in founding bounds for the probability that an occurring cluster of jumps is going to trigger a further jump. We proved the stochastic increasingness property of the duration tau n plus 1 minus tau n with respect to tau n with minus tau n minus 1. This property means that if this is large, so if we are at tau n minus 1 and we have to wait a long time before seeing the next jump, then we have to expect that the further jump at tau n plus 1 will be far, okay? Third, we found feasible bounds for some interesting probabilities interesting for us, accounting for the discreteness of the observations, which is exactly the problem we have at hand. We have discrete observations. So the discreteness of the observations introduce error, at least two types of errors in identifying the jumps locations. So errors in the implementation of our formulas. So exactly accounting for these errors, we found bounds for the occurrence of jumps in consecutive intervals. These can also be used, as we also did, to check whether our model matches correctly the data, the empirical data. Okay, so I start illustrating the first theoretical result, and then we will see if I will have time to go on. So we are interested in the probability that an occurring cluster of jumps is going to trigger a further jump. We fix a small epsilon, for instance 1%, and we consider that the observation time, we are at time S, capital S, between two consecutive jumps, okay? And we assume that at the observation time, lambda is far from lambda 0. We define this T epsilon S, which is the first T after S, when this quantity here, that I will illustrate in a few seconds, is below lambda 0, 1 plus epsilon. This quantity here is exactly the value of lambda t for all t after S and before the next jump. So the value of lambda t if no other jumps occur. Okay, so lambda S we start with lambda S far from lambda 0, above this level here. So T epsilon is the first time when lambda comes back to close to lambda 0, okay? Based on this T epsilon, we extend the definition of further jump. Further jump is not only a jump occurring when lambda is lambda 0, but when lambda is close to lambda 0, so less than this level here. And we define cluster plus a specific cluster of jump, the set of the jumps arrived when lambda is far from lambda 0, so above the level lambda 0, 1 plus epsilon. So T epsilon represents the end of the cluster, because after T epsilon, lambda is back below level lambda 0, 1 plus epsilon. So if we observe the cluster plus of jumps, of k jumps, for instance, we can name their jump time arrivals by tau L plus 1, tau L plus k minus 1. By definition of cluster plus, lambda was above this level during the whole period from this to this time, okay? So let us rename tau I like this, okay, and tau I plus 1 like this. So we observe the cluster up to this time, and we don't know whether this will still be part of the cluster or not. We want to know whether it is or not. So tau L plus K belongs to the same cluster we observed before, if and only if at time tau L plus K is still, lambda is still above level lambda 0, 1 plus epsilon. So, if and only if tau L plus K comes before the end of the cluster, okay? So our problem is, what is the probability that tau L plus K still is a part of the previous cluster? So the previous cluster did not exhaust yet because it is going to produce a further jump. Now, it turns out that T epsilon S and P are explicit functions of the parameters of the Hawkes process, the exponential Hawkes process. But they also depend on lambda S, so on the level reached by the intensity at time capital S. But lambda S depends crucially on the exact location of the jumps up to time capital S. So, using the closed formula for this quantity is not feasible. More realistically, we could know the level of lambda at previous moment u, for instance, when the cluster didn't occur yet, for instance, when the cluster didn't occur yet, it was probably it was a tranquil period, and probably lambda at time u was close to lambda 0. So we can have an idea about lambda before in a previous time, okay, with respect to S. And perhaps we are able to estimate the jumps occurred within the interval between U and S. We don't mind whether we have the exact location or not, okay? In that case, we can give a lower bound and an upper bound for the probability of our interest. I underline that Renaud, Boré, and Roy in 2007 also focused, like us, on non-asymptotic quantities about the exponential Hawkes process, a generalization, in fact. But they focused on estimation of the probability law of the length of a cluster. However, this is not useful for us because we want to estimate the end of the cluster for our aims. And if we know the length of the cluster, but we don't know the beginning point of the cluster, we cannot, this is not useful for us. Our alternative is using lambda u and the number of jumps occurred between U and S. This is our result. We call small s the length of the interval between U and S. A lower bound for the probability of our interest is this quantity here, okay? The upper bound we found is this quantity here. Okay, this is explicit. It seems complicated, but it is applicable. So how can we apply this type of results? We considered JP Morgan prices from 2006 to 2013. We have 5 minutes log returns, increments of log prices. We have 152,000 observations, a little bit more. These are the returns of JP Morgan. Note that 2008 September is just when Lehman Brothers had a default. So here you see that there were some turbulence before the main event, okay? So using truncated realized variance, it is possible to estimate the price jump. You assume a model for eggs, for the log prices, similar to like this, like the one I've shown you before, like this. Given a model like this, you can estimate the jump arrivals. First of all, we checked whether jumps were necessary to explain the behavior of the prices, the log prices. And in fact, we found that if we use the model without jumps, the fit would be poor. So you specification in this method here, we found 817 jumps on the whole period. So we call hat n the estimated counter of these jumps. We found that the increments of hat n are not independent. And that large clusters and we found large clusters in these jumps. So we guessed that a Knox model was proper to fit the jump times. And we estimated different types of OX processes to hat n. So exponential kernel, sum of exponentials as kernel, power kernel. And we found that the best fit was given by the exponential kernel with only one exponential function, the one I've shown you in the initial drawing of the lambda. In particular, we found alpha phi of 0 significantly different from 0. So self-excitation is present, is needed to explain the behavior of the jumps of JP Morgan asset prices. Goodness of fit test is, for instance, done using the property that the transformed integral of the intensity. So the increments of the integral from tau j minus 1 to tau j, as j varies, have to be IID exponential random variables of parameter 1. So we plotted the empirical quantities of these with respect to the quantities of an exponential random variable, and we found this cuckoo plot. Okay. Oops, I think I've... okay, sorry. Yes, okay, so we adopted this model. We found that this cuckoo plot was not that bad, and we implemented our formulas to the using the estimated parameters for this OX process, exponential OX process, for the estimated jump times of the JP Morgan asset prices. But we have estimated the parameters of the OX model from estimated n. So we have two types of errors. The error of the estimation of the parameters of an OX model and the estimation error in the threshold technique. So we wonder whether the accumulation of these two types of errors could render our formulas not useful. So we made a check of the reliability of our results, of our formulas on simulations. We simulated 500 paths of a process log or log price like this, where sigma is exponential of a mean reverting process, jump component given by exactly a process like this with an exponential OX model with the parameters we estimated above. The variance, the jump size are assumed to be Gaussian with this variance here, which is particularly small, but we chose this variance because in this way the model fits better the observed prices. So we simulated the path. For each path, we estimated the jump times, and from the estimated jump times, we estimated the parameters of the exponential OX model using maximum likelihood, as we did before. It turns out that the average percentage estimation error of the parameters lambda 0, alpha, beta is respectively about 20%, 40%, 50%. Nevertheless, with epsilon 1%, having taken two different intervals, US, by substituting within our formulas the estimated parameters for the true parameters, we find that the percentage errors in identifying the probability of our interest, the low bound and the upper bound, are of order 10 to minus 3. So it seemed a reasonably low estimation error. In particular, the estimated lower bound and upper bound are very close to the true probability. The percentage error is about, again, of the order 10 to the power minus 3. Now, what our formulas tell us on the data. So this is a report on the probability that an observed cluster of K jumps will produce a further jump. Observed cluster of K jumps on the interval US, knowing lambda U, okay, probability that a further jump will be produced by the occurred cluster. So as K increases, this probability increases. As the interval US is larger, the probability, okay, the probability decreases. But note that all these probabilities are quite close to 1. So the model tells us that the jumps are very persistent. In particular, the persistency parameter is beta. The exponential kernel has exponential of minus beta x. So beta, our beta is quite small, so the persistency is high. Okay, our beta is 9. It delivers a persistent process, jump process. Okay. So what time is it there? It is 12 minutes missing, right? Is it right?
Yeah.
Okay, so I skip this, but perhaps I have to leave the floor for questions, perhaps.
You may continue if there are any question. I mean, audience can ask in between also.
Okay.
But if you have some things to show, continue.
Okay, I will skip result number 2 because perhaps this is more interesting. We will see. So the result number 3 is giving feasible bounds given discrete observations for the probability of the occurrence of K consecutive jumps. So jumps in consecutive observation intervals. So we assume that we can observe n at discrete times. Now, in this case, we have 2 sources of error in identifying the jump locations. First of all, we don't know where exactly, if we detect a jump inside here, we don't know where exactly it is inside the interval. Secondly, if within the interval 2 or more jumps occur, we only can detect 1 jump. So we wanted to account for these type of errors. The key quantity here is lambda tilde n, the probability that within the interval n delta, n plus 1 delta, conditionally on the information up to n delta, we have at least 1 jump. I try to be fast. We have, for the exponential Ox model, we have an explicit expression for lambda tilde. But again, this expression depends on lambda n delta, which we cannot really observe, okay? Lambda n delta, due to the errors in the estimation of the jump locations, cannot be exactly reconstructed. So we produced a feasible forecasting of the next of a jump in the next interval. In this way, given lambda tilde n minus 1, we have that if there was at least one jump in the interval from n minus 1 delta to n delta, then the conditional probability of having one jump in the next interval from n delta to n plus 1 delta is within this interval. If delta n was 0, then we have an exact quantification of lambda tilde n, the conditional probability of the next of a jump in the next interval. So this result links lambda tilde n to lambda tilde minus 1, n minus 1. So we can apply it recursively and obtain the following results. The probability of the occurrence of a cluster circle, okay, meaning jumps in consecutive observation intervals, and also the probability, the conditional probability of the arrival of a further jump after a cluster of consecutive jumps. So we use different names, different symbols for clusters of different types, okay? Before we had a cluster of k jumps, but here we have a cluster of k jumps which are consecutive. Okay, so lambda tilde n plus k is exactly the conditional probability, condition to the present information, that a cluster of consecutive jumps occurred within the interval of within the interval from n delta to n plus k delta. We find that this conditional probability is contained into this interval, depending on lambda tilde n, so what we can say having the observations up to n delta, and the parameters of the Ox model, alpha, beta, and lambda 0. Lambda tilde 0 depends on lambda 0. So our empirical application produces this table where we can see the upper bound and lower bound for the probability of at least k consecutive jumps starting from n delta, conditional to lambda tilde n. So in the table, we see the bounds. We see in this column the empirical probability obtained from our data, empirical probability of having one jump, empirical probability of having two consecutive jumps, okay, at least two consecutive jumps, and so on. In the last column, we see the empirical probability computed from simulations, so of an exponential Hox process. So note that for k equal 1, all the probabilities are in line, same order of magnitude. For k equal 2, the bounds are in line with the empirical probability computed on simulations. This number computed from our empirical data is higher than what would be given by the model. But this is because in our data record, we have a huge amount of jumps occurring at 5 minutes distance. So two consecutive jumps, given the observations each 5 minutes, produces a lot of occurrences. However, among the 100 simulated jumps to produce this average number, there are some paths producing this amount of observed occurrences of two consecutive jumps. Okay, from k equal 3 on, we have this column with zeros, because this is due to the narrow, our narrow data, relatively narrow data set. So in order to produce numbers different from 0, we would need a much larger data set. So finally, given lambda tilde n, so we can compute we could compute the probability of at least one jump in the interval n delta n plus 1 delta, given that a cluster of consecutive jumps occurred up to n delta. This would be simply given by the quotient of the probability of the intersection of these two sets divided the probability of the conditioning set. So we didn't go further in this, but this could be done. The bounds that one could construct for this are different from the bounds we gave in the first result of our paper, because the former, the previous, the bounds given in the previous result didn't account for the discreteness of the observations, and in that case, the cluster could be of arbitrarily, the cluster could be constituted by arbitrarily sparse jumps. Here we consider consecutive jumps. Now, further research would have to be devoted to accounting for the jump sizes in the Hox model, because clearly the jump sizes could influence whether a further jump will be produced by a cluster of previous jumps or not. And also, a multivariate framework would have to be considered because clearly the jumps occurring in one asset could well influence the jumps occurring in other assets. For instance, when Lehman Brothers had this bankruptcy, a lot of other assets had huge jumps, downward jumps in their prices. So that's all. And thank you very much.
Thank you very much. So from the audience, are there any questions?
I wanted to revisit the definition of lambda, where they define the phi function.
Lambda,
The
okay.
definition of Fox process, I guess.
The initial
So where
part.
the jump process.
You wanted to see this?
Yeah. So
Okay.
yeah. So how is the definition of kernel? So the phi, how is defined here?
Phi, for a general Hawkes process, phi is a deterministic function from positive numbers to positive numbers, integrable with respect to Lebesgue, to the Lebesgue measure, and phi of 0 has to be strictly positive. Then my specification in this paper, our specification is that phi is an exponential function. Alpha, which is the jump of lambda each time a jump occurs, a jump in n occurs, times exponential of minus beta x. So these decreasing parts are exponentially decreasing.
Okay, yes, thank you. Got it.
Any other question? I can see many other students are also there. Okay, if there are no other questions, let us thank the speaker again for this very nice talk.
Thank you. Thank you very much.
Okay, so by this we end this